Okay, this is important. Okay, this is a cousin problem. The cousin hypothesis. The cousin hypothesis. The cousin hypothesis. It's basically about the genetic codec of systems. GitHub.com/OBNXS directed symbiotic birth control, um, directed symbiotic evolution, which is fitted to the cousin hypothesis. Um, 1 second. Yes, yeah, don't know anything. No, no. Yes, I need to understand that the cousin hypothesis is literally why we have neurodivergence probability. Basically, trying to solve the problem of neurodivergence using graph centrality and such as A-star algorithm and dashes or closest to closure. Degree of centrality is basically the measure of closeness or magnitude, like a vector component. To understand, it's a vector component you're measuring of a graph system. So you're measuring the magnitude of a graph. So that's the framework of graph centrality. So the magnitude has a direction, a rate of direction, and size. Size. So the magnitude is the size, the direction and size. But it's basically based on how close the system is, which means the meaning system has a meaning, has depth, or can propagate information. These are known as semantic graphs, but I don't really know how I've modeled them before. I just continue with the hypothesis. So the cousin hypothesis is that you don't have a disease. This is neurodivergent disability doesn't come from your family; it comes from your cousins. And the hypothesis proposes that having a cousin with neurodivergence and disability is because there's some kind of genetic combination on the other end of the tree that caused it. Not the family, not the in between family, because the in between family will be perfect. But they have a mirror opposite. So that's the first step. So I'm going to just record happens in the video. So you're gonna have your me, my dad, and my sister. Me, my dad, my mom, and dad. I'm neurodivergent, and but my cousin is not neurodivergent. And based on the features, the hand, kind of emotion they produce, and based on the genetic combination of the phenotype of genotype, the question happens to know a joke to me is basically the darker symbiotic evolution concept for the AGA system. What I call the artificial genetic system, which is called artificial genetic system, which is basically gives you which basically make sure you are born in time, basically on a time axis, everything's done right in time, or born in space. Basically have enough breathing rooms, which are two you need for perfect tissue for a human being. But this system has to preserve children that are being born in kind of born in war. Human training aid for war, and it's basically like incubator which have never been for Mother Nature. Everything that's Mother Nature is really where we come from. The cows, the cattle, incubation for Mother Nature. And us as mammals. But the problem goes to forms of mammals. So, I can't give you an answer. It's the algorithm, but the extra has a degree of magnitude. And the degree of magnitude represents the shortest path shows path algorithm, so it's algorithm. And the degree of the actual algorithm is the closest, more closest, but it's not faster than Dijkstra. It's basically, it's not, the Dijkstra is faster than Dijkstra, it's faster than Easter, but the Easter algorithm has its own benefits too. So there's some properties that are shared, but there are traits that are shared too, but it's not isomorphically solving the same, used to solving the same problem. So if you have a Hamiltonian graph, listen, for some people have an East algorithm, you should know that Hamiltonian graph, and because you don't have obviously you can draw the Hamiltonian graph without picking a pen. You can solve the problem, draw a graph like this the places where you're gonna be, and then you're gonna have the place you're gonna be, the place you're gonna be are gonna use to solve the curve pathways to join. And we don't have to pick. There's no picking up your pen, no picking up anything. You just walk. You can't teleport. cannot teleport. At least not yet. But the goal is system of non-linearity, you're gonna have the new dimensions. For example, if you have graph, if you have one family of descendants with Jewish dividends, and they're just opposite your family, that's degree one. That's closest one as well. Degree and closest one. And you're gonna have degree two, which is basically the two descendants of from you're gonna have say one descendant two. And by then you see the big differences, unless you're gonna have stability. Yeah, that's good. So you're gonna have a phenotype geneticity, like finding your hands, your function of the body, your soul, and the genotype and phenotype model of the system of disability, and being able to work with your body, your mind, control. Basically, I believe it goes down to the neuroprocessing level because you know divergence, but you also have to work with functional, so redundancy. I don't see any redundancy in the system, but if there's any redundancy, we have to get rid of it. But basically, we're born in time, born in stuff, we're both encoded into a CG, so you have to encode it so it can only appear again, as a framework of being born in time and done in born in space. So the direct symbiotic evolution is the concept that basically not GMO. Basically, you control it. You direct the birth of by giving it what I call pseudogenes, like genes that basically you're gonna give something genetic something. And you're gonna try to so the system picks out what it needs. The nutrients what it needs. The incubator picks what it needs. So that thing we call materials. The system, and when your body picks out something that's good, it will push all the bad stuff out. Basically, it's like because he has to determine what's good genetically. So it's called is. I'll go so many hours of this, but this is a video, short video. So let me go to my repository here and see what I can find out what I'm talking about because it's not gonna work out if I don't have this properly noted down. So the first one I'll start on is the DSBC, Directed Symbolution Evolution Model. Or basically, this one said is basically all men are man. A woman is a type of a woman is a term, but history you don't. So it's just a woman for men. Go to directed symbiotic birth solution repository, github.com /O for Oscar, B for Bravo, I for Indigo, S for November, E for Echo, S for Romeo, etc. You're gonna have that. Then you're gonna have directed symbiotic birth control. And this is basically the birth control model via directed symbiotic evolution. And basically you can control the birth make by using by observing and showing that that I know what I'm doing, but I don't want to say what I can disclose personally. So what I'm doing is basically trying to give you a framework for the system, guys. But this will come go to this video. This is very important to have business system. Basically, gonna have auxiliary space as solution spaces. AS2 splicing. So I have a CRISPR and have AS2 splicing. So if you go to AS2 splicing, you'll see that AS2 splicing. Let me read it out. Let me just get it. Yes, read it out to see what you guys think about it. To see what you guys think of this document. Oh, it didn't read out. Okay. AS2 splicing. Splicing. A class AS2 auxiliary space transformation, guys. Okay, what was it? 1 second, can you 1 second. So this one is really kid, this one framework. I'm not being kid, I don't want kid. So you have splitting, so splicing. So you're gonna have AS2 splicing, which is basically auxiliary space solution space splicing. So you have splicing or CRISPR. This is splicing. So CRISPR is was subregion. So obviously for subregion. So that's why CRISPR is not used here. But it's a gene splitting splicing protocol. It's not splitting because it's doesn't matter how advanced it is. This is what I'm saying. It's the sequence I'm using to do it, and we really have a system of system. So you're gonna have a quantitative system. So let me just find where system. So you're gonna have the methodology. So you're gonna have span frequency equals geometry. And sequence is literally a span lattice. So you're gonna have a span. A span is literally a sub range in a span. So you go a range which is like from 10 to 2, 10 to 2, 10 to 2, 10 times 2. So you have a range of square. A square is 10 by 10. 10 by 10 centimeters. Now, 10 by 10 centimeters is an area of a space you can splice. Now, let's say that can be split into subregions like 5 to 10. Now, 5 to 10 will be half of that. You do 5 and half is 5 or 10, 5 and 10, and that will give you an area, subregion. Now, that subregion is the lattice, which is ordered to be a lattice. It can operate, we also about a lattice, which is when genes are heterogeneous homogeneous. So, that's what lattice is encoded. Now, the span, basically, the definition of span is literally the range, the subrange of a lattice over a sequence. So you have a sequence, geometric sequence. You have 510, 510. That's a sequence of the area you're operating on via the gene sequence, like adenine, thymine, cytosine, guanine. You may think it's counterintuitive, but you have to work you know, respect the geometric structure that's really there, so you can operate on it, so you can operate with no problem. Because a span can skip. So if you get like think of a CSS span, span two, span space two regions, and then followed by another 5, 10. Can keep accumulating based on order of the lattice, just like that. So you're gonna have span two. So you have 5, 10. Span two will give you 5, 10. 1 to 5, 5, 6, 7, 4. 710, 5, 710. And that'll give you 710 area of grip. So that'll be 7 times 7 equals 49 centimeters area you operate on. And based on the geometry, it gives you precision. And the span has a range. And the range is basically the system of AS2 splicing. Because you can also splice sequences of genomic structure via an order. And the order is heterogeneous, homogeneous. So this is an operation table really of what's going to happen. This was born in time and born in space, but it's basically a philosophy of ensuring that you're dissecting the system, killing them. Doesn't matter if the pod is on the ground for 9 months on the ground. It comes out and you get a baby inside. You get a flu baby. Examples, this is a system of establishing not dominance, but human-centric governance. But you're gonna have a spline, you're gonna have a range, you're gonna have a tuple, you're gonna have, but these are operating procedures here. A tuple is a group. You're gonna have an indexing to each group. This is basically bound by group theory. So let me try to find this one. Biological computation. So what's this one? Get rough. There's get rough. There's no microOS sparse model. It's a sparse model first. So part 5. So closed loop with edges without edges. So, yes, RNA, if you go to the repository on AS2 splicing, you can understand, their RNA sequences are reader and writers bidirectional, and they are operational because, they are computational machines based on visa BVBO, but the read and write both actually they duplicate the read and write. So just got to go back to once the BVBO gets to the end, it's to start reading and rewriting and reading and write to the end until the operation is complete. So basically, it's a read and write of the genome statement, which is literally how BCBs that read the tape, or turn machine read the tape and go from one end to the other end and back. if until the competition completes. What else? Okay, thank you guys for watching this video. I'm gonna put it now. If you like my diary, like, share, subscribe, and share my TikTok too. At OBNexus and OKPALAN.